We've all been there, right? You want to build a nice, lean container image, but what you actually end up shipping looks a bit more like this. Today I'll show you an easy way to go from large, cluttered container images to nice, lightweight, distroless images without all the hassle that usually requires. But first, let me introduce myself for a second. I'm Nikolas. I'm a developer in the Garden Linux team at SAP. I'm usually the guy in the team fiddling around with bootloaders, file systems, that kind of low-level stuff. But what I'm presenting today is more a side project that has progressively gotten out of hand, and now here I am. So I just mentioned Garden Linux a second ago. For those of you that don't know that yet, that's our lightweight container-first open source distribution based on Debian. It's primarily intended as a Kubernetes Node OS, and it's the main distro of choice for SAP Gardener workloads. But since recently, we've also made it available as container-based images. And Garden Linux is also part of the NeoNephos Foundation. If you want to know more in general about NeoNephos, there's actually a panel discussion on that tomorrow, so I'd highly encourage you to go and check that out as well. Okay, with that context out of the way, let's do a quick recap about distroless containers. I guess since you're coming to a talk about distroless, you probably already know what it is, but in case anyone doesn't, like a quick recap. On regular containers, you have your base image that contains all the normal OS stuff, like a package manager, your core utils, your shell, all that stuff, and then you build your app on top. The idea with distroless containers is you get rid of all that base layer. So your container really is just your app code, whatever data it needs, and just the bare minimum required libraries. So distroless containers get you quite a lot of benefits. Primarily, it's just a smaller container. You have less stuff in there, smaller size, less storage, faster to pull the container image, all that stuff. But that's just one of the benefits. The other side is you get a way reduced attack surface. Like if there's less stuff in there are less vectors for an attacker that they can use to get in. And one point that's quite often overlooked, besides just in general a smaller attack surface, you also get way less CVE scanning noise. Like if there's less stuff in there, then like automated scanning tools, they're not going to find stuff you're not using anyways, but that you just happen to have in your image. And then you always have to like triage that away, say, no, it's a false positive, we're not using this. If it's just not in your container, you don't need to worry about that. Like one example, this recent sudo vulnerability. If your container is never using sudo, but it's still in there, you'll still get a scanning result from your tools. You'll need to triage that away. If you have a distroless container without it in there, you don't need to worry about all those. So distroless containers sound quite nice. We all probably should use them if we can, but how do you actually build one? Well, you start from scratch, like either completely empty container or one of the pre-made ones that start with like only a libc in there. You add your binaries, and then you publish that container, right? No. That's the point you realize, oh, I have missing dependencies, because the binaries I included linked to some libraries. I didn't include those. Well, not too bad. I look at what libraries I need. I add those. Now I can happily ship no. Missing dependencies again, because the dependencies you just added have dependencies on their own. So you add those, and they have dependencies on their own, and on and on and on it goes, all the way down to dependency hell. That kind of dependency hunting, that's like the main challenge when you want to build distroless containers, but there are also a couple more challenges that come along with it. Like one thing, debugging can be quite painful. Like if you want to debug some problem with your container, you can't just log in because you don't have a shell, you don't have core utils in there. Just mentioned 2 slides ago, that's the main benefit. Yeah, in production. The second you want to test or debug that benefit really quickly turns to a negative. And often what people then end up doing is they have one dev image, one prod image. The dev image is built on some regular container. The prod image is built distroless, but they're then no longer linked to each other, so they will drift apart further. 2 months down the line, you have 2 completely unrelated images. You have an issue in prod, you try to debug it in your dev container, doesn't reproduce there. So, not really great for debugging. So, what if we rethink that approach to building distroless containers? So what if we could have Like the nice, easy workflow that you get with regular, normal containers, but still end up with the nice, lean result of a distroless container. That's exactly what we try to achieve with Unbase OCI. With Unbase OCI, we're sort of flipping a script around. You start with just a regular base image, what you normally would use. Obviously, we would recommend you start with a GAN Linux base, but the tool works with anything. You can use Debian, Fedora, Ubuntu, whatever you want, like any regular base image. You then just write a normal, plain, standard Docker file. You do your regular commands in there. You can use your normal package manager. Like nothing about that needs to be in any way special or fancy. Just whatever you want to do, use your full shell, core utils, everything in that step. And after you've built that, you then just run Unbase OCI as the very final step to minify that image. And then you can happily ship that. You have a almost as good as Distroless, probably not 100% as small, but like 95% the way there with 5% the effort. Like it's really just running one command. I'll show that in a second. So before we get to the demo part, just in general, the concept, how it works. Consider your two container images kind of as sets. You have the base image, you have your app container. There'll be some large intersection. Usually the base image is actually a subset of the app container. In this example, let's imagine maybe the container file deleted some stuff from the base, so then there's stuff that's not completely a subset, but there's going to be quite a significant overlap between your base image and your final container. We identify all of this and we consider this for stuff that we ideally want to delete. Obviously, we can't just throw away all of it directly, so instead we identify what dependencies the added part of the app container has inside the base. We mark those as not to delete. And then we build the new distroless container out of just the stuff that your app added, plus its dependencies, with all the stuff of the base image completely dropped. Okay, with that we get to the demo part. Okay, here we have a demo container. It's just a regular container file that's installing Nginx, Node, FFmpeg. This is essentially an app that is some web app that lets you convert videos to animated WebP files, just as a nice example because it includes quite a lot of stuff installed there, so you have quite a fair range of moving pieces. It's not just a Node.js application, or not just the Python stuff, it's multiple moving bits in there. So we built that. I have already pre-built that, so it's just using the cache here, but just to see that is what is built from the container file. And if we run this, we get this here. There's a video file in there, just to show how the container works before we minified this. So this works as it should, but if we list those images, it's sort of large-ish. Like, could be worse, but could be quite a lot better. So now we use Unbase OCI to make this smaller. What those parameters there mean is the -L tells it to look for dynamic linker dependencies. Auto means we don't want to bother directly telling it what base image was used. It should just figure it out. Small note on that auto stuff, that only works if you've locally built the container image. If both the base and the image are pulled from somewhere, you need to explicitly tell it what the base was. It can only do that auto-determining if you locally built this. Then we're using the demo container we've just built, and we want the final one to be tagged as unbased as the output. So what this is doing right now is it's extracting the rootfs of both the base and the target, so the app image. Then it is comparing those, finding what files are different in there. It just finished looking for the dynamic library dependencies, and now it has removed all the stuff that we don't need from the app rootfs. And as we can see there, it has removed 86% of the base image, which resulted in a total reduction of 85 megs removed from the image. So if we look at those again, we see there the unbased variant quite a bit smaller. Obviously now you're questioning, does it still run though? I mean, I can make a nice small image, but if it doesn't work, then it's useless. So let's run that one instead. That one. Refresh this here. Get this in. And we see it still runs exactly as it did before, just with a reduced amount of size, without us having done any amount of work, besides like running one command. You didn't have to manually dig through what does ffmpeg need, what does Node.js need, none of that, just run a single command. So, let's look a bit more into like what it actually removed, what it kept, like where the size difference is coming from. Like here we have a before and after of exactly those containers we were just working on. Left side is just the one that fell out of the podman build command. Right side is after running unbase. Most of those look sort of similar. I mean, the largest parts are still libnode, some codec-related stuff that ffmpeg is likely using. Like that, all of that is retained. That was kind of to be expected. I mean, that's what we actually need to run our app. But on the left side, you also see like one thing, the bin directory that was 34 megs before, now it's just 6. So that stuff like bash is gone, core utils is gone, and a really large part is also all the Perl-related stuff is gone. Like this container was based on a Garden Linux base, which is derived from Debian. So like all Debian-based stuff, it always includes Perl. Obviously, if you can get rid of that in a container, quite a bit of a size advantage there. Also, like basically everything that was in var beforehand got completely dropped. So really, this is just what mostly just what our app added, plus the dependencies. So looking at those dependencies in detail, this here really is the complete list of every single file from the base image that was kept. Besides that, everything else in the final output container is just what our container file added. This is truly all that was kept. I mean, most of this is sort of obvious. I probably could have guessed that myself. Like, sure, we need libc, we need the GCC runtime components, but some of the other libs in there, I wouldn't have guessed that some component along the chain needs libmount, for example. I don't know why, but it figured it out, and I really wouldn't have wanted to debug that myself to figure out what exactly this list is. Okay, let's look a bit more at how this works. So the tool that I just ran, that's the unbase OCI command, that's really just a wrapper script. Like the tool that you're running, that's not doing any of the action really on itself. The main stuff is implemented in a container of itself. So the wrapper script is just instructing your container runtime to export the container image as an OCI archive, handling mounting those into the container. Container is then doing the magic, returning this to your wrapper script, and that's re-importing everything into your container runtime. Nice side note on that unbase OCI container, there we're actually dogfooding our own tool. So when we built that container, we first built a distro full version of it, and then we passed the distro full container into itself as an input to minify itself, and that minified version is what gets published. So that way we kind of already have a self-test in the build step of unbase OCI itself. So let's zoom in a bit on the unbase OCI container. So this is kind of the inside view of what it's doing. It's getting the two OCI archives as inputs. Those are then piped through an extraction step that's just looking at all the layers in the OCI, extracting them all, applying all the stuff that you need with like whiteout files and all that to like just get whatever the final rootfs of this container is. Put those two side by side. And then we're comparing those on a file basis. we're first looking at just the file permissions and users and that kind of stuff. If those are the same, then we're also comparing file content. We are fully ignoring any timestamp related stuff, because with containers, looking at timestamps, not really that useful most of the time. So really just looking at permission bits, owner group, and then obviously the file content if all those permission stuff is the same. And then all the files that are different in the app root.fs compared to the base root.fs, those go in the modified set. And then that runs into the resolve dependencies step, where out of that set we look at all files that appear to be any kind of ELF binary. Is that an executable, a dynamic library? Doesn't matter, any type. And we're resolving like what dependencies that has and identifying which of those live inside the base image part. Reason we're looking at all ELF binaries and not just as executables is, for example, stuff like PKCS11 modules or something. Those aren't executables on their own, but they're then loaded by things like OpenSSL at runtime, and the linker dependencies still need to be resolved. So that way, just looking at all ELF binaries is just a safer option to ensure that really everything still works afterwards. Then we combine the depend set with the modified set. That's all the files we want to keep. Those run into the final step where we're pruning the root.fs, and that step only keeps from the app root.fs what was truly needed. That goes all the way back through the chain, rebuilding an OCI archive out of this, and then it's returned to outside of the container. Okay, so who is this tool for? Like one of the use cases, obviously, I just shown, if you have containers that have multiple runtimes in them, so they are not just a plain, only a Python, only a Node.js container, but that have multiple tools all working with each other. You won't find a pre-made Distroless container starting with that. So you have to build it yourself, doing it by hand. So really this tool can help you quite a bit. Another use case is if you have a lot of legacy images, like let's say you have a ton of legacy images that are all massively bloated, you want to make them smaller, you don't want to rewrite them all from scratch, obviously, so this tool can help you to get most of the way there without having to rebuild everything. Or also if you're maintaining CI/CD pipelines and you want the dev version and the prod version of your container, this way you can ensure they're always in sync, because you will use one and the same container file for both, and then just the dev version gets the unbase OCI step afterwards. The prod version gets that, the dev version doesn't. That way you're 100% sure that both of them are always in sync. And like I just mentioned before, it reduces your amount of false positive CVEs, so for security teams it can also be quite useful. I'll be fully honest with you, like if you're already really well versed in building Distroless containers completely by hand, this tool probably isn't for you. It's not going to be as efficient. Like there'll be a couple bytes more in there. It's never going to be as efficient as if you really dig in and do it all by hand, but running this tool takes a minute, doing it all by hand, probably a couple days, so choose your trade-off, I guess. Okay, so this, all I've got left to say is go and try it yourself. You can find it there, give it a try with one of your own images. Small caveat on that. If you want to use this part where it fully works directly on images in your container runtime, like exporting this as an OCI, re-importing it, all those steps, that part currently only works with Podman. Just running it on plain OCI archives will work with Docker as a runtime, but the import-export part, at the moment, Podman only, but we're always open to contributions, so if you want to build in Docker support, you're more than welcome. Thanks. All right, I think we have time for questions. Yep.
Are you able to blacklist some files?
Yes. I'm not sure if it's on the recording, if you ask there. He asked if it's possible to blacklist files, and yes, you can provide manually both an include and an exclude list, and those will be considered like the include on top of all the modified files. And then after all those are identified, the exclude is applied, so all that stuff, even if it was modified, is still dropped. And if you provide stuff explicitly in the include list, that's also going into the dependency resolution step. So let's say you explicitly include bash, then all of its library dependencies will be pulled in as well. Yeah. Thanks. Yeah.
Since you did the root FSs, do you ultimately produce a single output layer, or do you somehow intelligently trace back to what the initial layers were?
Yeah, we're only outputting a single layer output to make it even. Well, like regardless how many layers the app or the base image had initially, they're completely written to just one rootfs, and then the output is always just a single layer rootfs. Yeah.
Because you initially made the vulnerability scanning case, I was wondering whether auto detection of the base image is still working after unbasing?
No. No, that's not going to work.
That would break?
Yeah.
And I was wondering whether you did an SBOM scan before and after the unbasing?
Haven't done that yet, but yeah, that's a good point. We probably should do that. Yeah, thanks. Yep.
Removing all the var files pretty much also break SBOM detection. For example, I know that things like Trivi read the Debian package DB. And SUMI will cut it out, so it will be hard.
Yes, like if your SBOM tool is looking at the DPKG database, then that will break completely because we are removing that entirely as it's not needed to run your app. Obviously, you can just allow this that. You can just add it to the included part that you want to keep the var DPKG stuff as a at a trade-off, obviously, of larger sizes.
But you will get rid of all vulnerabilities because there's nothing left from anymore.
I mean, it depends. Like if your scanner is only looking in there, then yeah, that's kind of tricking the scanner. But I mean, there are also scanners that just look at the binaries themselves. Those ones would still accurately produce it, but yeah, stuff that's just looking at the package index, that would break, yes.
If my entry point shell script uses bash and I do not install it in the container file, is it removed or does it?
Yes, but no, by default that would be removed. You would have to explicitly add it to say that you want to keep bash. Like we might add some auto detection of like scripts that use certain shells at some point, but at the moment that's not in yet, no. So at the moment, if you use shell scripts, you need to explicitly include which shell you want to keep. That's why in the demo, I can show this for a second again. We look at here again. That's why it's using S6 and exec line in order to start up both Nginx and Node.js so that we can start it with some command line arguments without relying on a shell to do that. So if you are using this, I'd highly recommend using those two tools in combination with it. That way you get around the need for a shell. But you can obviously still include a shell if you want to.
Thank you.
Ah, yeah.
If I select this or write this some file that shouldn't be removed, will it also keep the dependencies of those files?
Okay, yeah, the question was like if explicitly included or excluded files also resolve the dependencies, and yes. Like the include exclude is done in the first part, like it's doing the diffing first, then on top of this keep set, it's then adding your explicitly included files, then from there subtracting all the explicitly excluded stuff, and then it's doing the dependency resolution, so yes. Yep.
Considering that OCI images are anyway only tarballs, did you think about doing the whole thing without any container image runtime, container runtime at all?
I mean, you can, like all the stuff that's running inside a container is just a couple of bash scripts relying on several default utilities. Reason it's in a container is twofold. A, we don't need to give you a massive list of you need to have the following standard tools installed. And B, this way it runs both on Linux and on macOS if you have like this Podman machine stuff installed. It's just a way to ensure that we don't need to give you like a list of install the following stuff, make sure it's at least this and that version. It's just a run it in this container and it will work. If you want to go through all the effort of finding exactly what tools version to use, then yes, if I go back a bit to here, basically all of this stuff, all the steps in there, they're all basically scripts on their own, and inside the container there's an unbased OCI entry point script. You can totally run that entirely directly on your machine. On most machines, it should directly run. Obviously, the script has no like safety stuff in there that it detects if it's running with the wrong version of certain core utils, because the assumption is it's in this container, but I'd say like on 90% of machines, it should just run without a container around it. That's just there for your convenience.